Okay, today we will continue our discussion on FM generation and detection that we started yesterday. And to summarize our discussion yesterday, we learned that we could generate FM signals using two different kinds of methods, the direct and the indirect. We had a detailed look at the indirect method, namely the Armstrong method, and how it could be used in practice. Right? We looked at a typical commercial example that would be a commercial design for an FM transmitter, in which we had to choose an initial narrowband FM generator. We had to initially make a narrowband FM generator followed by frequency multiplication. Right? The narrowband FM generator generates a small modulation, a signal with a small modulation index. Frequency multiplication produces an FM signal of a wideband FM signal of a large modulation index. Right? In the process, the carrier frequency also gets multiplied, and to get the requisite carrier frequency, we may have to go through one or more stages of frequency multiplication followed by frequency translation. Right? So these are the things that we discussed yesterday. The advantage of using this method, you may ask why should we use this method at all? After all, we have to go through so many stages of operation. The main advantage is the frequency stability that is associated with the indirect method. Now let me explain what that means. So one of the main advantages of the indirect method is what we say frequency stability. Now this may look a little odd because we are working with we are talking about frequency modulation here or phase modulation here. Frequency and phase modulation are naturally associated with variation of instantaneous frequency. Right? So what do we mean by frequency stability? Whenever we have a transmitter or anything that modulates any carrier for that matter, for various reasons it is desirable that the carrier frequency remains fixed. Right? What do we mean by remain fixed? Basically what we are trying to say here is that it does not drift with time. You know, all electronic components are subject to electronic drifts, thermal drifts. Right? Because of temperature variations, there can be variations in the properties of the circuit, and one of the properties that one has to worry about in oscillators is the frequency of oscillation as a result of these drifts. For example, as I mentioned earlier, the frequency of oscillation is typically dependent on the resonant circuit, right, the LC components. The LC components themselves can keep on varying if there is a temperature variation, right, and that leads to a drift in the frequency, center frequency of the oscillation. Right. Now that is not desirable in any electronic system, because that will create, because for example, if there is a significant frequency drift at the transmitter and your receiver does not know it, right, then the receiver will get affected, and there are so many millions of receivers, particularly in a broadcast situation. Right. So it is very much desirable in many broadcast applications or communication applications to keep your frequency of operation fixed and don't allow it to drift too much. Typically fixed frequency of oscillation requires highly stable sources of resonant frequency, right, and typically these come from what are called crystal oscillators. Right. Crystal oscillators which use a quartz crystal in the resonant circuit, which electrically can be modeled as a resonant circuit, right, a parallel LC circuit, are very stable sources of oscillation. Right. If you use a crystal in the tank circuit, in the tuned circuit, parallel resonant circuit of a oscillator, it is a highly stable source. Right. Now once you start with a highly stable source like this, there is no way you can change its frequency. Right. Whereas in frequency modulation, what you require? A change in frequency. Right. So these are contradictory requirements. You can't use crystal oscillators in the crystal oscillators at the same time have variation in frequency. Right. Whereas the indirect method does not have this problem, right, because our starting point is not FM generation at all, it is generating like an AM signal, the narrowband FM signal generation is based on just the carrier and a DSPSC modulator, right. The DSPSC modulator has the a fixed local oscillator inputting which is being used by a multiplier, the other input being the message signal MT, right. The MT is being multiplied with sin omega CT and no direct frequency variation of is required. So, the local oscillator which is producing sin omega CT or cosine omega CT can come from a highly stable oscillator, a quartz crystal oscillator for example, right. So, that is what I mean by disadvantage. Your frequency, the center frequency of the carrier is not subject to drift, it is highly stable. It can be made highly stable by making use of a crystal oscillator as the starting point. After that you are just multiplying the frequency, right. You are not doing any further generation of the center frequency, right. So, that is the main advantage. Is there a disadvantage? Is this point clear? Why it is it will produce a stable frequency, right? Is this point clear? Now, what is the disadvantage? There is also a disadvantage which I think you should be able to tell me, which we have discussed briefly earlier. The disadvantage is that the narrowband FM generation is based on an approximation of the actual FM signal, right? Because we represent cosine omega CT plus phi of t by making we represent it in terms of quadrature components, assuming that phi of t is much less than 2 pi. There is an approximation involved here, and this approximation is quite good. For example, if you consider the design that we discussed yesterday, we made this condition, we chose this condition, this is of the order of 0.5, right. Of course, if this is of the order of 0.5 and this is, we chose this for doing this, we chose FM to be the lowest frequency component present in the message signal, which was of the order of 50 hertz, right.
So, what is taken to be lowest?
I am explaining that right now. The reason why we choose it to be the lowest is because if we ensure that this is small for the lowest frequency component, this will automatically imply that this condition that delta f by fm or phi of t is much less than 1 for the larger values of fm, right. So, it is definitely going to ensure that this is much less than 1 for larger values of fm of f sub m. Okay. So, as far as the larger as far as the higher frequencies are concerned in the modulating signal, for those frequencies the approximation will be quite good, right. We do not have to worry too much, but for the low frequency components present in the input signal, this approximation may not turn out to be very good, because it is not really much less than 1, right. We are still, it could be much better, but then if you make it too small, the multiplication factors explode and the design becomes impractical, right. So, these are the broad considerations which kind of require us to work with some kind of maybe somewhat poor approximation at lower frequencies, and that poor approximation leads to some kind of distortion. That is, the signal that you generate is not a pure FM signal, right. It is a slightly distorted version of the FM signal, because you are not generating this directly, you are generating something that approximates this, right, and that approximation is poor. That means there is a distortion, right. Typically, this distortion will take the form of undesirable amplitude variations in the signal, right, which original signal does not have. The original signal has a constant amplitude, but this approximate signal will have some amplitude variations. So, these are the pros and cons of using the indirect method, right. So, at lower frequencies there is a slight problem, but otherwise it is a very good method and one that is extensively used. As against this indirect method, let us now spend a little more time on the direct method. Or direct generation of FM. As I mentioned, the direct method can be based on either oscillators or relaxation oscillators, right? Resonant oscillators or relaxation oscillators. I will discuss here the case of the resonant oscillators. And just to to set the ball rolling, let me just draw some kind of a schematic diagram, schematic circuit diagram of such an oscillator. Okay. This is a schematic diagram. I have shown a transistor, but I have not shown many of the other components that this circuit will have. For example, the transistor has to be biased as an amplifier, right? So, it will have the biasing circuits. I have not shown any of that here, right? I am only looking at the AC model which is relevant for our discussion, right? So, this is let us say a transistor with some gain, some amplifier gain in the amplifier board, and there is a resonant circuit here, right, this parallel LC circuit. And as you can see, there is a feedback mechanism in this, right. These two inductors that I have shown, which are otherwise in series, this they have a mutual coupling which is shown by these dots, right, and that essentially means that if you take the output of the circuit as from here, if this is your output, or a portion of this output is also being fed again at the input through the coupling, right, and there is this that gets amplified, etc., and you have this oscillator building up, right. So, basically, as I mentioned, the basic principle, I am not really going into a very detailed discussion of how an oscillator works here, right, but the important point is there has to be a feedback. The feedback is, you can see there is a feedback path here, right, and that feedback builds up the circuit to produce an oscillation at a certain frequency, because this feedback occurs, this positive feedback occurs at the resonant frequency of the circuit, right. So, whatever is the resonant frequency of the feedback circuit, it is really the frequency of oscillation, right. So, other than that, I will not go into a detailed discussion. There are many kinds of oscillators. This particular one is called a Hartley oscillator. I am sure you will have a much more detailed discussion of the Hartley oscillator in your analog electronics course. So, and the oscillation frequency of this will be 1 by square root of LC, where L is this, let us say L1 and L2, L1 plus L2. In other oscillators, this feedback circuit will be in some other configuration. That will be the major difference from one oscillator to some other oscillator, right. The feedback mechanisms are designed to be in different configurations. Suppose this, let us assume here in the present discussion that such an oscillator is available to us. The question that we have to address here is, can I use this oscillator as a source of FM generation? If so, what do I need to do with this circuit, or what features do I need to have in this circuit so that this becomes an FM signal generator? Any suggestions for that? Would you like to make any suggestions? What do I need to do? I need to modify or make this frequency of oscillation voltage dependent, right. How can I make it voltage dependent? Some obvious answers are there, isn't it? I am sure you can produce one or two obvious answers, at least one obvious answer. You require a variable reactance of some kind, either your inductor L or your capacitor C should be made to depend on some applied voltage. It is as simple as that. Really, you have to think of the most simple solution that comes to your mind, and that is the obvious thing that comes to your mind. that if you want your oscillation frequency to depend on a voltage, basically the components which decide the oscillation frequency should be made to depend on the voltage, right. So, you require some kind of a variable reactance. Now, not only variable, I am not saying passively variable, but actively variable, that is voltage dependent, right. It has to have voltage dependence, right. Reactors or reactances which satisfy this property, which have this property, all are known by the name of varactors, variable reactors, right. Or if it is a if most of the time it's very difficult to find naturally occurring voltage dependent inductors, right. There are very few devices, hardly any that are known which have this property. On the other hand, a voltage dependent capacitance is something that you can easily build, right. So, most of the time these varactors are actually variable capacitors and sometimes simply known as varicaps, right. So, these are variable capacitors or voltage dependent capacitors. Okay. So, an example of a variable capacitor or a voltage dependent capacitor, does something come to your mind again? Would you like to suggest something that you know which can act like a variable capacitor or a voltage dependent capacitor? Any device that you know of? The p-n junction, the junction capacitance, right, the junction capacitance of a p-n junction, right. So, that is the most commonly form of the variable capacitance. So, junction capacitance, particularly the reverse bias junction capacitance, right, in the reverse bias mode. In the reverse bias mode, you know that the p-n junction has a depletion region, and across the depletion region you have a capacitance, right, and that is voltage dependent, right. So, junction capacitance of a p-n junction is an example. So, sometimes these p-n junction diodes which are specially used to exploit this property, they are designed to give you a good variation of capacitance with voltage, and they are known as varactor diodes or varicaps. Right. Now, the actual dependence of this capacitance on the applied voltage may not be exactly a linear relationship. It is typically a nonlinear relationship. There is a square root kind of relationship available, right. But let us assume for the moment that we have a linear relationship. So, basically what we are saying is that your capacitance C of this kind of a device varies something like this. It oscillates or it varies around some fixed value of the capacitance, right. So, C sub 0 or C sub O is the nominal value of the capacitance without application of an outside voltage, and as you apply an external voltage, it varies in this manner. So, if this is your message signal and you apply this across the reverse bias junction, right, this will create a junction capacitance which has, actually it will not be such a nice linear relation, but let us assume for the time being that it is such a relation. Actual relation may be a little more complicated than that, and we will discuss that separately. So, what happens to your frequency of oscillation? It becomes 1 by square root of L C naught into 1 minus k times m t upon C naught. I have just replaced C with this expression, taken C naught outside this expression, and that is how I have written it, right. And this, as you can see, can be written as 1 by square root of LC naught into 1 plus, now this is I am using an approximation once again, assuming that this fraction is small, right. I can write this as 1 plus kmt upon 2 C naught, because this is raised to the power minus half, and doing a binomial series expansion taking only the first term, you get this. Okay. If here we are assuming that kmt upon 2 C naught is much less than 1. This is nothing but, actually I should not call this omega naught now, I will call this omega, right. This factor is your omega naught as defined earlier, the nominal carrier frequency that you will get in the absence of a modulating signal when mt is 0, right. When mt is 0 you only have this term, right. So, this is omega naught into 1 plus, let me call this factor kf, k by 2 C naught, kf times, no, I will call it kf prime times mt, or let me call this as omega naught plus k sub f times, to put it in the standard form. So, your k sub f will be equal to k f prime into omega naught, right. And note that even when this condition is satisfied, kf that you have here, the frequency modulator constant, right, this proportionality constant can be quite large, even though this condition may be satisfied, right, because you are multiplying kf prime with omega naught to get your kf, right. And so, you can directly obtain fairly large modulation indices, because you do not have a restriction on kf, you have a restriction on kf prime, right. Because your omega naught is typically quite large, this factor is sufficiently large for us to obtain wideband FM directly. So, this is the principle of a direct FM generation method. In this capacitance is the crucial thing, variable capacitance or voltage dependent capacitance, which I said can come from a reverse biased PN junction. Okay. So, the principle is really very simple. Now, detailed design will depend on the design of the oscillator, and then you replace the capacitance in that oscillator with this reverse biased junction capacitance, and that is it, that becomes your FM generator. Are you okay with me on this? Okay. Now, what are the pros and cons of this vis-a-vis the direct method or indirect method? Any comments on that? Let us talk in terms of the factors that we discussed earlier. Namely, we consider two factors which were important when we discussed the indirect method. One was frequency stability, the other was distortion. There is no distortion here, right. If we have a perfect capacitance dependence like this, there is no distortion here, right. We get a perfect FM signal. Of course, if it is a phase modulated signal you need to generate, instead of working with M of t, you will work with the derivative of M of t. That will be the only difference, right. Otherwise, there is however, as far as frequency stability is concerned, what can we say here? Will it be as good? No, because we do not have a crystal oscillator here. The feedback circuit, the LC components are not coming from the quartz crystal, right. They have to be separately realized, because one of the components is the variable capacitance. In fact, that capacitance by its very name is variable, right, and therefore is subject to drift and all the effects that are associated with any passive component or active component in this case, right. So, all the drift effects will very much be present, and you cannot be sure that the omega 0 that you are going to get will be constant for all time, will not drift. So, the frequency stability is greatly affected in this case, right, and one has to use fairly sophisticated feedback systems to ensure that the system does not the system produces the required stability that you want from it. Even when you don't have frequency stability in the basic oscillator, it is possible to generate a complete system which has other components to make the overall system have frequency stability, but that becomes a very complicated system, right. I will not go into how an FM generator, for example, can be made into a stable FM generator, right, but it can be done, but that becomes very expensive. Okay. So, these are the pros and cons of the direct and the indirect methods. You have any questions at this stage? So, let me just comment. So, it produces advantages, produces wideband FM directly, right, because you can have a fairly large value of K sub f. The disadvantages that it has poor frequency stability by itself. However, it can be made to have the required, the frequency can be stabilized, stabilization is possible through an appropriate feedback system, which makes it quite expensive. If you have done some discussion on feedback, you must have also learned that feedback, particularly negative feedback, can be used to stabilize systems, right. So, one can design a special negative feedback system, control system of some kind, which ensures that even though there is a variation in frequency due to drift, its effect can be minimized, right. Okay. So, with this, I think I have given you a reasonably good idea of how FM signals can be generated. There is one more class of methods based on relaxation oscillators, but for lack of time I will not go into discussion of that. I would like you to read about it by yourself. Now, let us look at, let me return briefly before I go to FM detection, demodulation FM signals. I want to return briefly to our discussion on the bandwidth of FM signals, right. I want to return to it briefly just to emphasize a few points which I have already mentioned, but in a slightly different way. So, let us return to this topic. Basically, I want to have a good, you remember we drew the phasor diagram of AM signals when we discussed detection or demodulation of AM signals using the envelope detector in the presence of interference, right. It is important to have a feel for the phasor diagram of all these signals, right. So, this discussion, besides generating some other insights, will also lead us towards this phasor diagram that we are talking about, right. The first point is, so I will now do this discussion first for the case of general signals, because so far when we discussed the bandwidth issue, we did the discussion with respect to a very special modulating signal, namely the sinusoidal modulating signal, right. Let me take a general signal. So, let me define, since we are considering to start with FM, let me define A of t as the integral of m of t, right. So, your FM signal is A cosine omega c t plus kf times A of t, right. Is that right? Because FM signal is kf times integral of mt, which I have written as A t. The complex envelope of this signal what will be the complex envelope of the signal? will be simply e to the power j k f a t, right. This exponential function I can expand into a power series, right. E to the power x, I can write a power series for that and write this as a into 1 plus j k f a t okay, let me write one more term, minus k f square by 2 a square t and so on, right. And let me go back to the FM signal here. How will I do that? Multiply with e to the power j omega c t and take the real part of the product, right. If you were to do that, your original FM signal you can write once again. Would you like to prompt me? What will you get here? This will get multiplied with e to the power j omega c t and you are taking the real part of this part, this part. You will get simply cosine omega c t here, because 1 into e to the power j omega c t real part of that, right. What will you get here? J times e to the power j omega c t and the real part of that. This will become minus k f a t into sine omega c t, right. Then the next term will be k f square by 2 a square t, and once again you will get cosine omega c t, because this is getting multiplied once again with e to the power j omega c t and so on and so forth. So this gives you a different way or different look at the same signal. This is also a series expansion of some kind. Earlier also we had obtained a series expansion, but there are major differences in these two series expansion. This is a power series expansion. There we used a Fourier series expansion of e to the power j beta sine omega mt, because that was a periodic signal. This is not a periodic signal. A of t here is something arbitrary, right. That is why we have taken recourse to a power series expansion. This also yields some very good insight, some very good understanding, which we need to discuss a little bit. Yes, please. From here to here, this is a complex envelope. How do I get the real signal from the complex envelope? Multiply the complex envelope with e to the power j omega c t and take the real part of that. That is what I have done. Okay, that is the mechanism in going from here to here. I am assuming that by now you have quite experts in doing that. In any case, we discussed it and this is what we get. Now let us look at this expression in some detail. You find that the FM signal has, in fact it's quite clear that it's not a linear modulation at all, right, because you have terms like a t, a square t, a cube t, etc. Right. It was otherwise obvious that it is not a linear modulation, but this becomes more explicit now, right. So what can we say about the bandwidth of the FM signal, such an FM signal? It has this pure carrier component, right. There is a carrier component like we said earlier. Then there is this component due to this modulation. The bandwidth of this will be plus minus b around the carrier, right. The bandwidth of this component will be plus minus 2b around the carrier. The term corresponding to a to the power nt would have bandwidth of plus minus nb around the carrier. So as you can see, since this is an infinite series, theoretically the bandwidth is infinity, right. So this once again shows that theoretical bandwidth is infinity, right. Your spectrum contains various components. there is a components due to the unmodulated carrier, right. That is the first term. Then the spectra of AT, A square T, etc. translated around the carrier or translated to Fc. These are the various components that you have. So that shows that it has got infinite bandwidth. For the narrowband FM, we know that we can approximate it by only the first term in that expansion, and then that's it, right. But let me discuss it again. In particular, let's assume that MT, your message signal, is a linear combination of two sinusoids. It's sum of two sinusoids. So let MT be K1 cosine omega 1t plus K2 cosine omega 2t. If it was an AM signal or a linear modulation, you will get components after modulation at omega c plus minus omega 1 and omega c plus minus omega 2, right. Now in the case of FM, you will get components. Can you tell me now what components you will get? So for AM, the components will be omega, this basically omega 1 and omega 2 get translated to omega c plus minus omega 1 and omega c plus minus omega 2. For the case of FM, now not only you will have omega c plus minus omega 1 and omega c plus minus omega 2, but you will also have omega c. Now look at, I want the answer to come from the floor. Look at the nth term of this expansion, right. You remember when we discussed nonlinear systems briefly, we discussed that it generates additional frequency components. For example, a to the power nt will produce not only n omega 1 and n omega 2, will also produce their sum and differences, right. So you will have the most general form of these various components would be omega c plus minus n omega 1 plus minus m omega 2, where n and m are suitable integers, or they can be any set of integers. These are the intermodulation terms that the nonlinear components produce, right. So the FM therefore generates, like any nonlinear system, intermodulation frequencies. Okay. However, if we go back to the series expansion and say that the assumption that KFT is much less than 1, right, then once again we can approximate this series expansion by the first two terms, right. So if the assumption that we normally make for narrowband FM is valid, right, so if Kf AT magnitude is much less than 1, then your XFMT reduces to A times cosine omega Ct minus Kf AT into sine omega Ct. How will this be different for the case of phase modulated signals? Simply this AT will get replaced with MT, right, that is the only thing. Okay. Let me finally spend some time. So this, I hope you get a different insight about the spectrum of the FM signal. This analysis does not help us to obtain a mathematical expression for the bandwidth, right. That was not the objective of this discussion, right. The objective was simply to appreciate better what will happen to the spectrum, what kind of spectral components you will see when the input signal contains more than one frequencies, when the modulating signal contains more than one frequencies. You will not only get omega c plus minus omega 1 and omega c plus minus omega 2, but also the so called intermodulation terms, right. That was the important point that we really wanted to appreciate from this. The last point in this connection that I want to discuss is the representation of the FM signal in terms of the phasor diagram, particularly for the narrowband FM, right. It is difficult to look at talk about the phasor diagram of wideband FM at this stage. We'll come to that also. It's not really that difficult, but we'll come to that at an appropriate time. Right now let's look at, because it will be interesting to see, because the FM and the AM signal, narrowband FM and the AM signal have similar spectra, how do their phasor diagrams differ from each other, right, and how do they physically generate different kinds of signals, right. They have similar spectra and yet they physically generate different kind of signals looking in the time domain. Their looks in the time domain are different, right. One is a constant amplitude signal whose frequency varies, the other is a amplitude varying signal, right, even though their spectra are very similar, right. So we look at the comparison of FM and AM, particularly narrowband FM. So let me call this AM and narrowband FM. Both of them have a carrier term, right. Both of them have the term cosine omega ct, right, pure carrier term, and sidebands center at plus minus omega c. That is the common picture, omega c plus omega 1. Let us for this discussion, when we talk about phasor diagram, typically we talk of phasor diagram when the input signal is once again cosine omega mt or sine omega mt, right. We are going to look at that situation. So that means you have plus minus omega c and you have plus minus omega c plus minus omega m, right. These are the components which are present in the AM signal as well as in the narrowband FM signal. These are the only frequency components which are present, right. In what way the spectra are different, we need to appreciate that. In the FM signal, or let us talk about the AM signal first. In the AM signal, the sidebands and the carrier, they are in phase with each other. If you remember the expansion, you will have cosine omega ct plus mt times or mt times cosine omega ct again. That these are not quadrature carriers, right. They are the two carriers involved here and here, they are in the same phase, right, whereas the two carriers involved here are in quadrature phase, right. So in FM spectrum, or let us say in AM, sidebands in some sense, in the sense that I just mentioned here, they are in phase with the carrier, okay, whereas in the FM case they are in quadrature phase, they are phase shifted with respect to the carrier, right. You can think of this term as the sideband producing term, this as a pure carrier term, right. Sideband producing term has a carrier which is in quadrature with the pure carrier term. Basically that is what we are trying to say. So sidebands are phase shifted by pi by 2. Let us see what is the effect of that on the phasor diagram. If this point is clear, it should not be very difficult let's revisit our phasor diagram that we drew for the AM signal. Remember, we are talking about a rotating plane rotating at an angular speed of omega c radians per second, so that your carrier phasor looks like a fixed vector of length equal to the amplitude of the carrier. So, this represents your cosine omega c t, a cosine omega c t, right, and the two side bands are the components omega c plus omega m and omega c minus omega m, and with respect to this fixed phasor they will be moving phasors, rotating phasors, one moving let us say anti-clockwise and the other moving clockwise, right, and the resultant phasor at any time is the resultant of all these three factors, right, and where will this resultant always lie? It will lie always along this line, right. As these phasors rotate symmetrically around this phasor, the resultant of these two will always be on this line, and therefore the overall resultant will always go around the fixed amplitude of the carrier here, right. This phasor will, the resultant phasor will move along this line around this nominal amplitude. Okay, that is the phasor diagram that we discussed earlier for the case of the AM signal. How do the things change now? You have the same carrier as before. The only difference is that this rotating phasors are now associated with the term sine omega c t, right. So, at t equal to 0 they are in quadrature with the carrier components. So, their rotations, the clockwise and anti-clockwise rotations can be represented like this, and for these two rotating phasors where will the resultant lie? It will lie perpendicular to the carrier phasor always. As they rotate, the resultant of these two phasors will be somewhere on this line, right. At this point it is here. If they are somewhere, if they are here, the resultant will be somewhere here, right, but this resultant will move like this, right, and what will the overall resultant look like? Right, your overall resultant will have different positions like these. As these two phasors rotate and this resultant phasor moves up and down, the overall resultant moves in this region, right. And what do you see now? If you assume that this amplitude is not very large, this variation in amplitude which is visible here would not be very large, right, because these variations will be small. However, there will be an angular variation, right, and this angular variation is what causes angle modulation, right, and it also makes clear why that condition is required for it to be a good approximation to MT to the FM signal, right. The condition is required because if this amplitude is small, then the amplitude variation associated with this resultant phasor would be negligible, right. On the other hand, if this is not small, there will be a considerable amplitude variation as well, and there will be therefore distortion of the signal that you will generate. It will not be the pure FM signal, but FM signal with some amplitude variations as well, and also even this will not be a very good representation of the variations that you actually want to see from an FM signal, proportional to the message signal entry, right. So, this is the phasor diagram of the narrowband FM signal. So, unlike the AM signal, which the resultant is only varying in amplitude, here the resultant is varying in amplitude as well as in phase, and we are only hoping that the amplitude variations can be minimized by using the approximation that kf is much smaller than 1, not kf, yes, kf is much smaller than 1, beta is much smaller than 1. each of these will move in a circle, right, and the resultant will keep on moving like this. Okay. So, that is this you please keep in mind when we are discussing FM in some context where we need to use the phasor diagram representation. Okay. So, I wanted to start the discussion on the FM demodulation also today, but I think our time is up and we will start the discussion on FM demodulation next time. Thank you very much.